So I was wondering if we could automate this process, and to what extent we could automate this process. So here is our vision, right? So it will be great if we have some kind of secure, security critical embedded computation. For example, a C code that implements crypto algorithms. And we use automated formal analysis and synthesis techniques to automatically detect vulnerabilities and to repair them, the so-called countermeasure synthesis. And of course, formal verification, and we can collaborate with domain expert to evaluate the residual leakage in real device. So let me be more specific. If we consider the classic, for example, crypto code on smart cards, you have input, you have output, and you have some kind of side channels. Power, for example, timing, e-emission, and you have a lot of the other architectural level side channels and fault injections. If you look at the power, in front of this audience, I don't need to go into details because these are all well-known stuff. But you could actually perform this kind of attacks. What I'm more interested in this context is what is the threat model, or more specifically, what's the leakage model? Because if you give me the leakage model, the right one, I can do a formal analysis. And another thing that I'm interested in knowing is in practice, how do people mitigate this kind of vulnerabilities, and see if I can automate this. It turns out for power side channel, in particular, there's some well-established theoretical foundation for doing this. One is masking. It can be traced back to information theory or the secret sharing and all that. But at the code level, what you say is people are introducing random bit strings to scramble the computation to break the statistical dependency between the secret data and the side channel leak. So here is a very oversimplified wheel. You have this leaky computation. If the leaky computation is linear, what I mean is linear with respect to XOR operators in the Boolean domain, then what you can do is you can, before you give the sensitive data to the leaky computation, you randomize it with a random bit string. And whatever goes into the computation, even though it's leaky, it's randomized. You do want to get the correct output. So you take the random bit string, you push it through the same computation F, and that's FR, and then you XOR it back. So this is the ideal situation. Of course, this works only if F is linear, right? In practice, most of the crypto algorithms are not linear. So what ends up happening is that you have to hire some experts to rewrite your design. So here is a more concrete example. Let's assume that this is a piece of C code with 3 inputs, Boolean inputs. I1 is the secret. I don't want you to know whether it's logic 1 or 0. But you can observe the power consumption fluctuations, which is related to the logic bits in N1, for example. So here is the truth table. I have I1, I2, I3 can be from 0, 0, 0 all the way to 1, 1, 1. And this is a secret bit. I don't want you to know whether you're in the first half of the truth table or the second half. But you can observe N1. So if you measure the power, you would see the difference. So that's the leakage. And what people end up doing is they use some cheap generated random bits to scramble the computation. You still have the same 3 inputs, the same 1 output, but in the middle, all the intermediate computation results are scrambled and masked. So if you build a truth table for them, you see 50-50. It's a balanced number of logic 1s. So as a verification expert, when I look at this, I got excited because if the program is small, you could do this manually. But if the program is large, remember the truth table, the size of the truth table is exponential in the number of the logic bits, right? So you can have gigabytes of size of the truth table. So obviously, you need software tools. So that's what we did. The first thing we did is to build a verification tool for this. I won't go into details, but basically we use logic formulas to capture the number of logic ones in the first half of the truth table and the second half of the truth table. And then we do model counting. Maybe this is only interesting to me, but for classic form verification, where you, for example, try to do assertion checking or equivalence checking, there you typically would transform the program, the problem into a satisfiability problem, where you use set solvers. But here, it's fundamentally different because you need model counting. You need to count the number of solutions for each Boolean formula. And there are a lot of people in my community working on this kind of model counting set solvers. And what's more interesting in this case is we not only need model counting, we also need differential model counting because we want to compare the number of logic ones in the truth table. So from there, once we can detect the vulnerabilities, we can try to repair it automatically. Suppose you don't have the money to hire an expert to rewrite your code. Can we use a compiler-like tool to automatically do this kind of transformation? Right? So this is an instance of program synthesis, which is a hot topic in my community. So we've implemented a very simple version of this, and we've tried it out on some of the existing designs. So this is one particular implementation, reference implementation, where experts already handcrafted the mitigation, but we feel we tried our tool, we can automatically synthesize a version, which is different, which is actually smaller than their ones. And of course, we can also do form verification, and we collaborate with domain expert, for example, Patrick, and we download the software into devices and measure the residual leakage. So if we say it's formally verified, is it really formally verified? So we've done some preliminary work in this domain. But the big picture is really that there are all sorts of side channels in this domain. To me, as long as this community can give me an accurate or give us an accurate leakage model, we can do all sorts of formal analysis, synthesis, compiler-like transformation. So that is what I feel a very interesting research direction. So our long-term vision is to have some kind of a compiler tool. This is not a normal compiler where you type in GCC, you hit the return, you expect the result in less than 1 second, right? This may run a few hours, but this is fully automatic. So we can have all sorts of side channels. You give us the source code, an annotation of the sensitive data, some architectural level parameters, and we can automatically generate the implementation. That's all what happens.
Thank you. Hi, I'm Julian from the University of Pittsburgh. So we have been talking a lot about the trade-off between performance and security strengths yesterday. So our recent work directly addressed this issue. We are looking at how you can achieve better performance while running a very heavy and computing-intensive information leakage, defeating information leakage on data access panel. So as we all know, in multi-tenancy model in cloud computing, this provides shared resources among multiple users because they are all dispatched to shared hardware resources. And this exposes multiple attack surfaces, including the processor, the server process itself, the memory, and the bus, and et cetera, et cetera. So if we can use a secure processor, or we can use encrypted memory data to protect the processors or the memory, and reduces the risk to data breaches. But there are still side channel attacks, such as the exposed memory address access pattern that can be observed by the attacker. And This is the famous example on how you can observe the address sequence and then derive the algorithm, the control flow of the algorithm, because they are very regular, and then you can directly tell from just the memory addresses from the address bus. But by the way, you don't have to really physically tap on the address bus to detect this sequence. People have studied various methods on deriving the data access patterns, such as comparing memory data images at different times, and then you can derive at what location what data have been accessed. So there have been a comprehensive approach proposed to attack this information leakage. The original version is called oblivious RAM, ORAM, which essentially says that when you access the memory, you can obfuscate it in some way such that every access looks like sweeping through the entire memory address space. And this is very secure, but obviously it's very expensive. And later, it has been improved, and a less heavier method was proposed. So in this case, it's called a path ORAM. The memory address space that you want to protect is first organized into a tree structure, and all the data is stored in the nodes of these trees. Okay, so and all the data in these nodes are associated with one and only one path, and this path starts from the root and all the way to the leaf. Okay, so for example, the data in this intermediate node can be mapped to either path 2 or path 3, but only one path. So whenever you want to access the data, you first look up on chip from some position map to find out the path number of this data, and then you go to the memory and read out the entire path, read it on chip, and store it into on chip internal stash, and then you decrypt it, assuming the memory data is encrypted already. But then you internally you decrypt it, and then you perform your access, either read or write. And then after that, you actually remap your target data A here to a different path, okay, from path 2 to path 3. And then you write back the path you read from the memory by shuffling them. You re-encrypt and shuffle them. And then you write it back. So this path will actually look very different from the previous path. But then this data A is remapped to a different path, so later on, you will write it back to path 3. Okay, so this is how path ORAM performs, and we can see that every memory access is translated to one read and one write of the entire path. So this is this reduces the complexity from OFN to OF log n, where n is the memory space that you're protecting, but still is quite memory intensive. So what happens is that when such kind of application, you want to protect it using path ORAM, when such kind of application is dispatched to cloud, and then because the cloud is shared resources for many users, okay, you could be co-locating with other non-secure applications without memory protection. So you could run maybe a single secure application with path ORAM protection, but other non-secure application without any protection. So obviously you could generate a lot of traffic that deprive all the memory bandwidth you have on this particular system, which is unfair to the non-secure applications, and their performance could be greatly hit. So for example, you could, on average, the non-secure application in orange could be slowed down by quite a bit, and the worst case is really bad. So we looked at this problem and see that, okay, obviously, such kind of performance hit is generated by all the mix of memory traffic from both secure and non-secure applications, and non-secure application suffers because most of memory traffic are generated from the secure, from the path ORAM of the secure applications. So you could come up with some solutions. For example, can you separate them onto different memory channels? So for example, a server is usually has usually multiple memory channels, let's say 4. Can you put the secure application on a single channel and leaving the rest of 3 for the non-secure application? This is okay, but the thing is that if you limit the secure application on a single memory channel, then you remove all the parallelism for that secure application. So PathORAM benefits from being run on multiple channels because of the parallelism you can leverage, because you have so many reads and writes. So once you remove all the parallelisms, the performance of the secure application definitely is hit by a lot. Okay, and you may say that, oh, can I add more memory channels, more memory DDR memory channels? But then more memory channels are limited by the CPU pings, because every single parallel memory channel consume more than 100 pings. Okay, so that's very limited by the process itself. Oops. For some reason, there's one slide that's missing here. Sorry. I don't know what attack that I'm experiencing. I'm missing one page. I'm missing one page here, but okay, I can talk without that page. That's actually a pretty important, I don't know, so that, that's weird. I was just having that on my laptop, and it works fine. So that's actually a very important page, the most important. So the solution is that we can use a different architecture, memory architecture for servers. You know, we cannot isolate between secure and non-secure applications. We cannot add memory more channels, but we can leverage a different organization called buffer on board architecture. So buffer on board architecture is used is a very popular memory organization for server or cloud servers. So instead of using parallel memory channels, the buffer on board uses serial memory channels. So the parallel memory channels uses a lot of pings, but serial memory channel is more narrow than parallel channels, but then the serial links has a high frequency. So you achieve equivalent memory bandwidth, but then you occupy very few pings. So the buffer on board design is very good for expanding your memory capacity, because you can have one interface, one buffer on board interface connecting with the CPU, but then after this interface you can connect them with multiple parallel channels. So we propose that we can offload the heavy computing part of this ORAM. This is the main computing of the PathORAM or ORAM controlling part, and you can offload this part to the buffer on board architecture, and then this processor only connected with the rest of the memory from that buffer on board controller through the serial link. And so the figure will look very different because everything is offloaded. So from the CPU standpoint, the burden on the CPU computing is going back to normal, because you only talk with the buffer on board controller through the serial link. All right. Anyway, so once it's offloaded, then the computing is you cannot see this computing on the processor, but then everything is still performed, and then the secure application is still protected. And we developed a sequence of technique to mitigate the PPAP, mitigate the PORAM, PathORAM, performance, because we are. Oh, sorry. So 1 minute. So let me just skip all those technical details, and then I will move on. So yeah, I was actually mentioning this. So yeah, this is the second the problem that we are looking at. So the scaling number of applications, so buffer on board actually applies here. Once you have the performance issues, and then you want to see that, what if I have more non-secure applications and more secure applications, and with the traditional memory channels, then these traffic are still mixed together. So so this is the buffer on board. So let me skip to the rest. Yeah, this is the buffer on board. Okay, it's here. So it's a little bit messed up, but that's okay. So this is the buffer on board architecture that I was mentioning. When you offload everything, this part is serial. and then this is still the original parallel memory channels. And then among parallel memory channels, you can run both secure and non-secure application as usual, and you can use the performance improvement technique that we developed previously, and then this part, the non-secure application are running as usual. But then for the secure application, so let me move on a little bit faster. This is the buffer onboard benefits and why the serial link is faster than the parallel links, and then it has less interference. So when you have more non-secure applications, you have these benefits. The CPU is alleviated because it doesn't perform any secure operations. But then you can still maintain all the parallelisms for the secure applications. And then there's no modification on the DRAM links. So that seems to be a viable application for the path-over immersion. But you may still need to run your applications on both, both this buffer onboard control part and the non-secure application. This is the DRAM, regular DDR interface. So in other words, you can run both secure application and non-secure application on this channel and this channel. But then you have to think about once your memory capacity, if your memory capacity here increases, which means that your tree of the password increases, then you don't have enough of these resources here. What happens is that you could still leverage the remaining regular DDR interfaces over here. And the trick is that how you actually divide the trees, the tree you build for the memory. You cannot split the trees like the left children and right children and then put them on two different channels. But the way you split the tree is that you can do that in level by level. So if your tree gets expanded with one more level, that's doubling the tree capacity or the memory capacity. You can put it on the regular DRAM interface, because if you need to access the tree nodes over here, there's only one memory access, but you get to fetch the leaf node that you need. Okay, so this is how you share the hardware among secure and non-secure applications. But then this has very minimal performance hit to both type of applications. Okay, so let me conclude. So we found that interference between protected application and non-protected application is very challenging, and scaling them is even more challenging. And our experience is that if you can offload the entire computing to a non-CPU, in our case, it's buffer onboard design, then you can minimize the interference among both types of applications. So I have any questions to end
All right, thank you. All right, so I'm going to talk about the hardware-centric aspects in design methods for quantification and mitigation of information leakage. And a longer title. What I want to talk about first is mitigation techniques, and then later on I will look at leakage quantification. And I'm just going to give you a very brief overview as much as possible within 10 minutes. Okay, so we have a bunch of classical countermeasures. Essentially what we're looking at, and this is basically motivated from the way the attacks work, we are trying to look at leaked information from intermediate states, right? Typically, there's a long computation going on, and focus on one area of the computation to extract keys. And this has been traditionally just done in this way, and if there's no protection, this is rather an easy process, but we have techniques such as hiding and masking. So these are the most popular two techniques. These are sort of classical countermeasures that have been used for a long time now, over a decade. So what are these classical countermeasures? In hiding, we typically use a noise generator of some sort, so heavy use of random number generators. Execution orders may be randomized. You can use dual ray or asynchronous logic styles. I mean, there was a little bit of discussion yesterday on those, right? If you can do the circuit level, the IC level encoding such that it's independent of what is being computed on. Problems is some signals remain, these are not foolproof. They're somewhat heavy, like especially door-ray asynchronous logic styles and also different kinds of circuits, IC techniques. And resynchronization may be a problem in the computation path if you're doing these randomized computations. Masking is the other classical countermeasure, very effective. And basically what you do is you hide your data by adding random masks throughout the computation path. And there are different types of masking. You can do higher order masking as well. Problem is leakage still remains. Masks also leak at times, and it's not foolproof, but it's another standard technique, mitigation techniques. And in general, both of these techniques, or especially if you want to push them into the realm of most effectiveness, then they remain costly, and none of these are foolproof, and all of these counters can be overcome. Of course, we should qualify and say that that's given enough many traces, given enough many effort, and so on. Okay. So, and then there are some techniques that have been inspired more from, let's say, theoretical cryptography, and I'm not going into ORAMs or homomorphic now. Those are, especially homomorphic, considered more expensive for a lot of the applications. But there are simpler techniques that we can apply, and these are actually in use already in cryptographic circuit design in chips. Secret sharing is a standard technique. I'm not going to dwell on this. Basically what you do is just take a secret, let's say K, that you want to hide. What you do is you break it into shares, right? You pick random mass xi and then just XOR it over progressively to obtain these single shares. And what you're doing by doing this is splitting the secret K into n different computation paths, and if you can compute with them separately to mimic the original computation, then you're able to do the computation by masking. You can also, of course, this is the simplest case, let's say, the simplest instantiation, if you will, of classical Shamir secret sharing. If you want to do more than, if you don't want to do the first order, you just XOR the data together, but instead you want T of them to be able to recover the secret, you use standard secret sharing, but this time you want to implement it in the computation path. You need to make sure that your computations still work, right? The addition and the multiplication, the XOR and the AND and all of that. So you need to recode the computation path. And nice thing is, even if you have corrupted results, you can still combine a subset, of these together. And another way of looking at it is if you have, let's say, invasive attacks in your circuit, right? You can say, okay, with this many probings, the circuit will still survive, right? And T and N sort of give you a way of quantifying that. Okay. So problems in hardware, glitches are a major problem. Signal transitions before settling and so on, they have been known to be leaky for forever since this whole side channel area started. And it results in leakage of unmasked intermediates, so masking is a countermeasure. And of course the power model, there was a little bit of discussion in the first speaker today, right, where you can. All right, so another standard technique that's very effective and has become quite popular in the last 6-7 years is threshold implementations, and they're very effective, especially in lightweight cryptography. And basically what you do is you apply the secret sharing idea on the circuit, and what you're trying to do is split it apart, the data, like take the secret sharing idea, apply it on the computation path, and then you have to change linear and nonlinear computation blocks to reflect the shared computation. And the nice thing is, if you do this properly, even with a first order simple linear splitting like this, you can get prevention against first order DPA leakage. Okay? Here's a graph. I'm going faster, okay? And you see an unprotected Simon implementation on the left. and all of these are different key hypotheses, each trace here. And then you see the red one is the real key. It starts sticking out, even just a small number of traces, a few hundred traces after that. This is Simon implementation, right? Starts spitting out. And test vector leakage assessment is a way of actually assessing. It's a statistical technique that's used. And you see beyond 4, p-value of 4, you have the leakage appearing. And then here's a protected implementation using a threshold implementation, and the red curve is contained within the traces in the ensemble, right? And you see the test also fails here. It's a nice demonstration. Very recent, actually, 2015 results. TI in practice, so threshold implementation in practice provide a fairly reliable implementation technique. Significant area overhead. Redesign is a problem. You have to redesign S boxes and so on. So maybe the tools community can help there. That's a question. Consumes a lot of additional entropy, random bits and so on. And there's protection against forced order DPA, and tolerates linear combinations of leakages. And higher order attacks still succeed if you use moments and so on. But that means you have to use a lot more traces, of course. So there's a trade-off. And there are new results now, where threshold implementations are proposed to prevent higher order leakage. So you do higher order threshold implementations. Methods for leakage detection. So what we want to do is, of course, you want to mitigate, but there's still be some leakage and you want to assess it. It's much easier to detect leakage than to recover a key, right? And so detection has become more and more important, especially for certification and so on in the last 5-6 years. Mutual information analysis has been used successfully. It's pretty strong. It gives you quite reliable results. It needs a lot of data to converge. That's the downside of MIA. Template building is another way of actually detecting leakage. Just think about template attacks, and you essentially build profiles and templates and then verify. But you need to build the templates first, and then collision attacks. It's a cell profiling attack, already used. Disadvantages does not work for single bit leak, so it has limitations. And all right. And then finally, the TVLA test has been pretty successful recently. I'm just out of time, so I'm not going to go into it. But it's an adaptation of the t-test to the device under test model, for side channel quantification. The graph I've shown you before of the threshold implementation of Simon is an example of that, where you have the data sticking out, beyond 4, right? Here. And basically, you divide your data into groups. There are test vectors. There are different types. There are 3 different types of verification, and then you do statistical testing, and you look at the p-value. If it's beyond a certain bound, you say it's leaky, and how leaky it is. You can define a metric by taking that confidence value, right? So I'm out of time, I know, so I'm going to stop here. Right? Yep, 10 minutes.
Thank you both.
Sure.
So we have, in the interest of time, we have to be short on the Q&A session. So we'll have about 5 minutes of it. So we'll invite all the speakers. And people who are asking questions, please sign up. It's easier.
So I have a question about the performance of the compiler tool. So directed to the first speaker. So I would say from industry, I've worked for Broadcom, NXP, I've worked for Marvell, and now I'm with Analog Devices, right? I think the biggest gap that we have in industry generally is that tools, right? Pre-silicon testing tools, we have very few tools. You're right that we do everything manual, right? And if this was built as part of our flow, our CAD flow, we would be very, very happy, but Synopsys doesn't have it, Cadence does not have it,
There are very few tools. There may be one tool out there that does fault attack detection.
Right.
That's pretty much about it, right? So we do encourage this. I'll say that this is something that we all look forward to coming from the industry. So I won't speak for Roll and Divya, but at least from the rest of the companies, it's like we want this. Now, performance-wise, right? You mentioned the long-term vision. Like you guys are working on that. So how does the performance compare, right, to non-side channel protected? Because you're doing like simple power analysis protection there, right, by doing masking. And I think that would be like a first baseline that we all want to move towards in the future. So how does that performance compare, right, with non-side channel?
I don't know which part you're interested in, but this can be implemented as part of the CAD tools. So we actually have a paper a few years back on trying to resynthesize the circuit, the logic gates, to eliminate the timing set channels. So you have the different delay paths. If you overclock, and some of the glitches will be introduced, causing fault. So there we actually can beat the current state-of-the-art tool. Sometimes you can synthesize even a smaller circuit, but the tool will run a longer time. Like I said at the very beginning, I mean, when you use a normal compiler, GCC, right, you hit enter, you expect to see the compilation right away. But this may take overnight, but if it's a very important piece, I assume that maybe you want to wait a little longer. For software, we are actually automating things. We're not really inventing new mitigation. So if you could do this manually, we're just automating it. The performance, the runtime performance will be similar. So we're just implementing things in, for example, like Halloween compiler. Right now, what we're doing is doing that.
So is there any work looking at protecting against different types of side channels and then how they affect each other? So for example, if you look at power versus timing, right? If you try to protect or mitigate the power side channel, how does that affect the timing and vice versa? Because eventually you need not only to protect against information leakage in one dimension of the side channel, but the other side channels as well. And then you need manual techniques to combine them, which later on you can verify more formally.
Yes, and this since the beginning of side channel, 20, 15 years now, there have been proposals, and immediately we have seen side effects. Like one of the early proposals was dual ray, for example, right? Using dual ray encoding, where you encode a bit by putting data on two lines, and you say 1, 0 or 0, 1, right? To encode the implements. And the first comment that came out, I remember, was a chess at the time, Ali Shamir, raised his hand, spoke up and said, well, yeah, but you have a beautiful antenna there now. So the EM signature is improved, right? So, and we have seen this over and over again in the side channel community, where you had power countermeasures, let's say fault countermeasures, for example, with error correction, right, to prevent faults or having them detected, fault injection attacks. Those have the same kind of effect. They increase the leakage typically, right, unless you do it carefully, because you're spreading your data, your signal, right, over a larger piece of data. So the power signature is amplified there. So all of these effects need to be carefully accounted for. It's not as simple as building a tool and then hitting a button and boom, it gives you a side channel protected circuit. It's very subtle. It's not an easy thing to do.
Yeah, I think this is a great question. I've heard about this kind of question very frequently. Every time I talk to people, they would say, "Oh, you have timing, you have power. How do you?" So I feel that different people must have been thinking about different solutions. From my standpoint, if the different mitigation can all be done at the software level, for example, during the compilation, then it's actually possible to have a cooperative optimization. So basically you have multiple constraints specified upfront, and then you do a operative optimization inside the compiler. It's more like a super optimization with constraints. That might be possible, but I think in general this is the question, or one of the questions in the field is very difficult.
Okay, if there are no further questions, let's thank the speakers.